ba 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 director. Man, what am I doing? Hello, and welcome back to another exciting episode of Mr. Bell Physics. Today, first of all, don't adjust your screens. Don't feel like there's anything going wrong right now. It's actually supposed to be pitch black. This is me doing this. And the reason why it's pitch black in here is because right now we are doing our light and optics unit. And today we're going to be doing a demonstration that requires it to be pitch black in here for you to truly be able to see the effect. So, what I'm going to be using today is a device called a light box. Now, this light box is basically just a fancy box with a projector in it that really is just going to shine 3 different lights at the whiteboard, which is behind me right now. Those colors being red, green, and blue. This is all to show off something called additive color mixing. Additive color mixing explains how our eyes see light. So if I plug in the box, which I'm going to do blind, so bear with me. All right, there we go. What I could do is I could turn on individual colors. For example, blue, like so. Green, like so. And red, like so. Now, it turns out our eyes actually only see the colors red, blue, and green. Every other color is some combination of those 3 colors, which is really weird. So, let's combine some colors. The nice thing about this light box is that it orients the lights in a way that they actually overlap at points. So, obviously, no colors, no light being emitted, means that we're going to see pure black. And black being the total absence of light. Let's see what happens when I mix red and blue. As you can see, I get this nice kind of purple color. Technically speaking, this is a shade of magenta. Which makes sense. This lines up with what we would expect from art class. So let's turn off the blue. And we're going to turn on green. Now, you may think that is going to be a lot like mixing red and green paint. When you do that, you kind of just get this brown blah. But the thing is, light behaves very differently to paint. Because adding red and green together actually creates yellow, believe it or not. Now, this may not seem like it makes a lot of sense, and that's okay. The difference is that this is a process called additive color mixing. Whereas what you're used to, mixing different paints and things like that, is called subtractive color mixing. We have to remember light is either reflected or absorbed by any given surface. This whiteboard is totally white, so therefore it's reflecting all light. The combination of all light is white. However, my Boston Red Sox hat, the spring training hat, is primarily red. So, when I say turn off the green light here, not that, nope, there we go, and hold my light and hold my hat in front of it, it appears red. Because the fabric of it is red. This makes sense. In the same way that someone wearing a green sweater is absorbing all the other colors of light except for green. Now, the last color combination is just to mix blue and green. And when we do that, we get this nice cyan color here. Then, finally, if we combine all 3 together, like so, we get this lovely kind of tri-circle diagram with white light existing right in the center. Hopefully it comes up well. Hopefully there's not too much glare on the camera or anything like that. There's not much I can do about that. Now, to kind of show what I mean by reflecting versus absorbed, what I have here are just some pieces of paper on cardboard of different colors. So here I have the color red. And I'm putting that right into white light because that's what we would see normally. Now, this looks perfectly red to me. I can take another piece of red and I can put it on the red light. And unsurprisingly, I still see red. Okay, I'm shining red on red. But when I move this down to, say, green, it actually becomes black. The reason for this is that this red piece of paper will only ever reflect red light. It is not being hit with any red light right now. So therefore, it has nothing to reflect, which means we see black, a complete absorption of color. If we move this back up to yellow, which is a combination of red and green, we would see red. Because red is part of what makes up yellow. The same thing happens if we move this over to blue. We see black. Move up to magenta, we see red. Move it down to cyan, we still see black. And we can do this with the other colors as well. Let's do this with green. Okay, if I put green on green, it looks green. I put green on yellow, still looks green. Put green on cyan, still looks green. I put green on blue, it looks black. I put green on red, it looks black. I put green on magenta, it looks black. Because there's nothing for it to reflect here. And then finally, I could also do this with blue. Okay, blue on blue, looks blue. Blue on cyan, looks blue still. Looks identical to our neutral blue here. Blue on magenta, same thing. As soon as I move blue on to red, it looks black. Yellow looks black. Green looks black. Now, this is cool and all. But it also makes you wonder what happens when we look at these colors, magenta, yellow, and cyan. You may be familiar with these colors if you have ever bought printer ink. A color printer usually will be labeled CMYK, cyan, magenta, yellow, and black. That is because these are the three colors that are primarily used in subtractive color mixing. Now, unfortunately, I don't have the materials on hand to demonstrate that. But whenever your printer is operating, it is only ever using these three colors. All that your printer is doing is just using them in differing amounts to trick your eyes into seeing different colors. If you don't believe me, let's take cyan. Okay, cyan right in the middle there is a lighter shade of blue. Obviously, if I put this on cyan, it still looks the exact same. But if I move this on to blue, I only see blue. If I move this on to green, I only see green. And the reason for that is because cyan is the combination of blue and green. It will reflect both of those colors. But because it's only being exposed to one of those two colors, it can't possibly reflect both. If I move this up to yellow, it still looks green. Because green is part of yellow. If I move this over to magenta, it'll look blue. Because blue is part of magenta. The only color where this will look completely black is red. Because cyan isn't made out of red. The same exact idea applies to magenta and yellow. Let's do magenta. Okay, magenta goes right in the middle there. Put it on magenta, it looks like magenta. It looks the exact same as it does in white light. If I put it on blue, it only looks blue. If I put it on red, it only looks red. If I put it on yellow, it looks yellow. Or it looks red. My bad. It's been a long day for me. If I put it down on cyan, it looks blue. If I put it on green, it looks black. And then finally, we can do this exact same thing with yellow. Yellow goes in the center, right there. Looks perfectly the exact same. Move it up to red, I see red. Move it down to green, I see green. Move it over to cyan, I still see green. Move it over to magenta, I see red. If I move it down to blue, I see black. Now, that kind of shows off how we reflect objects, but it doesn't really elaborate in terms of absorbing color. That's what we're going to do now. What I have here in my hands are various color filters. I'm going to try to get them in frame here so you actually see them. These are filters specifically designed to only allow certain colors of light through. They absorb all other light. So for example, this is a red filter. So if I hold this red filter in front of the projector, we should only see red. And that's exactly what happens. We only see red. If I do the same thing with green, I should only see green, which is exactly what happens. If I do the same thing with blue, I should only see blue, which is exactly what happens. Okay, the reason why we see a little bit of green here is because this light box is a little bit oddly calibrated. It's a cheap light box. Tell my high school to pay me more to buy nicer supplies, or tell them to give me a bigger budget. Not much I can do about that, unfortunately. But what's really interesting is when I start to work with cyan, yellow, and magenta. See, cyan, remember, is a combination of blue and green light. So when I put this filter in front of the light box, only the red part of the tri-circle diagram goes away. Kind of trippy. Magenta, only green goes away. And finally, yellow, only blue goes away. Now, our eyes have various cells in the back of them called rods and cones. And the reason why they only detect red, green, and blue is because the cells themselves only detect red, green, and blue. So anything that emits light, right, any screen, every single pixel on that screen, here, I'll actually stand in front of here so you can see me a little better. Any pixel in front of that screen is actually just a very, very tiny red, green, and blue light. Each of them showing differing amounts of light depending on what color they want you to see. All of this is kind of trippy, but it has to do with how we actually end up seeing stuff. So, that's all I have for today. I hope that you enjoyed the video. Make sure to absolutely smash that like button. And as always, I will see you in the next video. Leave any questions you got in the comments. See you next time.